Imagine a world where drying clothes is no longer tied to electricity. A world where the simple act of hanging your laundry could become entirely self-sufficient, powered only by magnetic forces and smart airflow design. Today, we are exploring a concept that could redefine domestic energy uses a magnet-powered clothes drying system. Unlike traditional electric dryers, this system relies on Overunity principles, harnessing the unseen potentials of magnetic energy to generate airflow without consuming a single watt of electricity. At the core of this idea lies the principle of magnetism. Magnets exert a force that can be converted into motion, and motion in turn can produce airflow. In a typical electric fan or dryer, electrical energy is transformed into kinetic energy to move air across wet clothing. But what if we replace the electric motor with a system of carefully arranged magnets and moving parts that generate the same airflow naturally? The challenge lies in designing a system where magnetic fields are not just decorative, but functional, where they interact in a controlled way to produce a continuous and directed airflow sufficient to evaporate water from clothes. Testing airflow without electricity requires precise observation and measurement. Airflow is the movement of air in response to a pressure difference or a force. In conventional drying, fans push air to increase evaporation, and heaters speed up the process by increasing the air temperature. In a magnet-powered system, the goal is to create motion in the air without heat or electric input. The first step is to set up a rotor or pendulum that can spin or oscillate freely under the influence of magnets. Strong neodymium magnets can be arranged around a central rotor in such a way that their repelling and attracting forces create a rhythmic push and pull. Each oscillation of this rotor moves the surrounding air slightly, and with careful design, these small movements can add up to a noticeable breeze. One fascinating aspect of this setup is the use of Overunity principles. Overunity refers to systems that produce more usable energy than the conventional input, often drawing from unconventional sources like magnetic fields, ambient energy, or environmental interactions. In this context, Overunity does not mean violating the laws of physics, but rather using energy that is already present in a system and converting it more efficiently into airflow. Magnets, for instance, store potential energy that can be released when configured to interact dynamically. By creating a system where magnets push against one another and against moving parts in a looped cycle, it is possible to generate repeated motion without external energy. The design of the drying system is critical. It must ensure that airflow is concentrated where it is needed most. Wet clothes require consistent air movement around each garment to encourage evaporation. In a magnet-powered system, vanes or fins attached to a rotor can direct air along strategic paths. These vanes catch the movement from oscillating magnets and channel it through the drying area. Multiple rotors can be synchronized so that they create overlapping airflow patterns, increasing efficiency. Even small adjustments in the angle of the fins or the placement of the magnets can significantly improve performance. Experimentation is key, and each iteration teaches us more about how to harness magnetic energy for practical purposes. At this stage, one might wonder if such a system can compete with electric dryers in terms of speed. While it is unlikely to match the high heat and rapid drying of conventional machines, the magnet-powered system excels in sustainability and cost-effectiveness. Clothes dry more slowly, but the system consumes no electricity, produces no emissions, and can operate quietly. In many situations, slower drying is an acceptable trade-off for free energy use. Moreover, creative designs can enhance airflow using chimney effects, natural convection, and heat absorbed from sunlight, further accelerating the process. Understanding airflow dynamics in this context is essential. Air movement is influenced by pressure differences, friction, and temperature gradients. A magnet-powered rotor introduces motion, but it is the interaction with surrounding air that determines how effective the system will be. By observing the behavior of small particles, such as lightweight threads or smoke, it is possible to map airflow patterns and identify areas of stagnation. Adjusting rotor speed, magnet placement, and vane angle can then improve coverage. Testing different configurations systematically allows for optimization, creating a system that is not just functional but efficient. Another intriguing component is the integration of passive energy sources. Sunlight, wind, and even temperature differences can contribute to the airflow in a magnet-powered dryer. A well-placed solar panel, for example, can heat certain surfaces slightly, creating a natural rise in air that complements the magnetically generated movement. Outdoor placement takes advantage of wind currents, while indoor setups can exploit temperature differences near windows or heaters. In combination with the magnetic rotor, these passive inputs enhance overall airflow, demonstrating that multiple free energy sources can be combined in a synergistic way. Magnet-powered airflow also raises questions about long-term durability and maintenance. Unlike electric motors that can overheat or wear out, magnetic systems have fewer moving parts subject to friction. Bearings and pivot points still require occasional lubrication, but the absence of electricity reduces the risk of component failure. Furthermore, magnetic forces remain stable over time, meaning the system can operate for years without loss of efficiency. This makes it particularly suitable for off-grid applications, emergency preparedness, or regions where electricity is scarce or expensive. From a scientific perspective, building a magnet-powered clothes drying system is an experiment in energy conversion. It forces one to think about energy not just as electricity, but as potential, kinetic, and environmental forces interacting in harmony. By carefully observing how magnetic energy translates into motion, and how that motion affects air, we gain insight into the subtle workings of physics in everyday life. Each trial is a lesson in optimization, teaching us how small adjustments can yield significant improvements in performance. Now, imagine testing such a system in practice. Start with a small model, perhaps a single rotor mounted on a frame with clothes hung around it. Monitor how long it takes for clothes to feel dry to the touch, noting airflow patterns and rotor speed. Experiment with different magnet strengths and rotor configurations. Add multiple rotors in parallel to see if overlapping airflow improves results. Introduce lightweight vanes or fins to guide the air more precisely. Each modification offers insight into how energy is moving through the system and how it can be harnessed more effectively. The magnet-powered clothes drying system is also a gateway into broader experimentation. Once comfortable with magnetic airflow, one might explore other Overunity applications, such as water circulation, small fans for cooling, or even mechanical clocks powered by magnetic oscillations. Each experiment builds on previous understanding, expanding the range of possibilities for low-energy or zero-energy devices. The skills learned in observation, measurement, and iterative design are invaluable for any aspiring free-energy experimenter. Finally, consider the environmental impact. Traditional electric dryers consume significant amounts of electricity and contribute to household energy bills and carbon emissions. By replacing electric dryers with magnet-powered alternatives, even partially, the cumulative effect could be substantial. It is a small step in a larger movement towards sustainable living, demonstrating that innovation does not always require complex electronics or expensive infrastructure. Sometimes, the most elegant solutions draw from the fundamental forces of nature, like magnetism and airflow. Testing a magnet-powered clothes drying system without electricity is not merely a technical challenge. It is an exercise in creativity, patience, and understanding of physics. Each experiment, each iteration, brings us closer to a future where everyday tasks rely less on conventional energy sources. It is proof that curiosity, coupled with careful observation and persistence, can transform simple ideas into practical, eco-friendly solutions. As you reflect on this concept, imagine a laundry room where the hum of an electric motor is replaced by the silent motion of magnets, the gentle swirl of air guiding wet clothes to dryness. This is a system that rewards experimentation and encourages thinking beyond the ordinary. It challenges assumptions about energy, motion, and the ways we interact with the world. And most importantly, it demonstrates that free energy is not just a dream, but a field of practical experimentation waiting for anyone willing to explore it. In conclusion, a magnet-powered clothes drying system is more than a novelty. It is an invitation to rethink domestic energy use, a playground for Overunity experimentation, and a practical step towards sustainability. By testing airflow without electricity, observing patterns, and iterating on designs, one gains not only functional results but deeper insight into the forces that surround us. The potential is vast, limited only by imagination, ingenuity, and persistence. For those passionate about free energy, this is an opportunity to explore, experiment, and innovate in ways that could reshape how we think about power, efficiency, and daily life.